Thank you very much for waiting. We'd like to start Ruby World Conference 2020. The individual, the prize, Ruby prize, is for the recognition of the people who joined the Ruby community and started in 2013. And those who are to be recognized has been recommended from all over the world, and Ruby Association and Japan Ruby Association and the Matsue City forms the organizing committee for the selection and examination. And the Ruby Prize 2020, Jeremy Evans is recognized, Miura Hideki, Matsumoto Sotaro are finalists. Today, the, we'll, we are going to hear the presentation of Jeremy Evans, the winner of the Ruby Prize.
はい、こんにちは。松本幸宏です。Ruby コミュニティのですね、
Hello, Matsumoto Yukihiro. This is a prize for the individual in the Ruby community. And last year, he was also selected a finalist, and Jeremy Evans, and two more finalist nominee, Miura-san and Matsumoto Sotaro-san, were selected as finalists. Jeremy Evans was selected as a finalist, and this year is a prize winner, and two more have made a great contribution to Ruby community and Ruby. Prize is given to the individual, but in the case of the open source, there are some names of the software attached to it, and they tend to be project-based. But finally, each one of the individuals work on this the project and the program. Therefore, the software is being developed by these individuals in the context of the Ruby. In order to recognize these people, the Matsue City sponsored this prize and started. And we have a lot of applications, and we had very severe, the serious examinations, and the finalists were selected, and the prize winner were selected. In the past, it was called the Newcomers Prize, but now it is renamed to Individual Award. So those who are nominated for the Ruby Prize will be recognized and praised. And I hope that these people would continue to work for the contribution to the Ruby community.
Ruby was born in 1993. Since then, it was loved by many engineers around the world, and numerous systems and services that made with Ruby brought tremendous benefits and utility to many companies and people. But not many people know that Ruby's improvement and its increasing functions are thanks to the support by individual volunteers in the Ruby community. So we decided in 2013 to establish the Ruby Prize to award those who have made a great contribution to the development and dissemination of Ruby. Ruby Prize is awarded to those who have made a great contribution recently in the Ruby community. We believe that giving a due recognition to those who have made a contribution to the dissemination and development of Ruby will lead to further activation of the community, and thus more utilization of and a greater possibility of Ruby itself. This year's winner is Jeremy Evans' son. I understand that he made a great contribution to the development of Ruby 3, which would become available very soon. And also, Niure-san and Matsumoto-san, final nominees, made really great contributions as well. On behalf of Matsue City, which supports Ruby's further development, I would like to express deep respect to those three people. Lastly, I will extend my heartfelt appreciation to Matsumoto-san, Ruby Association, Nihon Ruby no Kai, and everyone who support Ruby Prize. Thank you.
Konnichiwa, Ruby World attendees. I'm sure many of you feel like I do, and that we wish we could be experiencing this conference in person. Unfortunately, that is not possible this year due to the global pandemic, but I hope I will be able to see you in person next year. First, I would like to express my appreciation to the Ruby Prize Executive Committee. I was deeply honored last year to be selected as a Ruby Prize final nominee, and even more honored this year to be selected as the Ruby Prize winner. I only hope I can continue to be worthy of this recognition. My name is Jeremy Evans. I became a Ruby committer last year on Endo-san's recommendation. One of the big changes I focused on last year was implementing the separation of positional and keyword arguments, which is fully complete in Ruby 3. Other than that, since becoming a committer, I have mostly focused on triaging and fixing bugs that have been filed in Ruby's bug tracker. Now, one of the privileges of being selected as the Ruby Prize winner is the ability to give a presentation to the attendees of Ruby World Conference. In my presentation, I'll be discussing some of the changes I have worked on this year to improve Ruby's object model. These improvements were all the result of fixing bugs that had been filed in the bug tracker, many of them years old. You can currently test these improvements in Ruby 3 Preview 2, and you will be able to benefit from them on the 25th when Ruby 3 is released. One of the most significant improvements to the object model in Ruby 3 is that calling include on a module affects modules that have already included the receiver. So let me show you an example of what that means. Here you have a module named eachString that defines an eachString method that yields values as strings. For convenience, you want to include this module in enumerable so that the eachString method is available to all classes that include enumerable. This should allow you to call the eachString method on a hash, since the hash class includes enumerable. And in Ruby 3, this works correctly, with each value being yielded as a string. Now this does show that hash each yields a single array argument with the key and value, and not the key and hash as separate arguments. Kanashi kana, in Ruby 2.7, this raises a no method error. And that is because before Ruby 3, including eachString in enumerable does not affect classes that have already included enumerable. So starting in Ruby 3, when you include eachString in enumerable, Ruby looks at all classes that have already included enumerable and adds the eachString module at an appropriate point in the ancestor chain in those classes. Now the historical reason that enumerable include did not affect the hash class was that originally Ruby did not keep a reference in enumerable that it was included in hash. So there was no way to easily find the classes that had already included enumerable. Charlie Somerville implemented an optimization for method cache invalidation in Ruby 2.1 that added this tracking, so that when enumerable was included in another module or class, enumerable kept a reference to that class or module. That list of references is what Ruby 3 uses to find all of the ancestor chains where the each string module needs to be added. So at the same time I implemented the module include fixed, I worked on the exact same fix for module prepend. Unfortunately, I was not able to commit that fix at the same time, and not because the fix itself was wrong, but because the fix exposed that there were many issues with internal classes called origin I classes, which module prepend uses. So one issue was that when a module with an origin I class was included into a class, the origin pointer in one of the created I classes was set incorrectly. So here's an example showing the problem. Here we create a class named A with methods M and M3. We also have a module M, which prepends an empty module and also has a method M that calls super and a method M2 that calls M3. We only prepend the empty module to force module M to have an origin I class. Then we have a subclass of A named B, which includes module M and then aliases method M to M3. When we call the M2 method on an instance of B, it should call this M2 method, which calls M3. We alias the M method to M3 in class B, so this should call the M method, and the method it should call is the one in module M. So this M method just calls super, and since this method is defined in M, and M is included in B, it should call the M method in the next ancestor. And that's this method in A, the superclass of B. And that is what happens in Ruby 3. This method returns the string M. Kanashi kana. In Ruby 2.7, this raises another no method error. That's because in the M method of module M, the super call here cannot find the super method because the origin pointers in the I class were not set correctly. So fixing the origin I class pointers was no small feat, since setting the correct origin pointer cannot be done when the I classes are created, since the origin I class does not exist at that point. So we needed to add a stack to keep track of the I classes, so that when the origin I class was created, we could set the origin pointer correctly in the original I class to point to the origin I class. So making that change caused non-deterministic failures in garbage collection. So the garbage collector needed to be modified to treat the origin I classes differently. It also caused virtual machine assertion failures. So the virtual machine needed to be modified to treat the origin I classes differently. So all of that to fix a seemingly small issue, but this was a necessary step. The next bug fix was making this code work. Now this code does not even use prepend, but fixing it used an approach that fixed other issues that allowed module prepend to affect existing classes, including the receiver. So we start here by defining a module M and a class C that includes it. We then define a module R that refines module M to add a method and then uses that refinement. We then create another class named A that also includes module M. Then you try to call the method added by refinement R on an instance of C, and this should work because C includes M and R refines M. And in Ruby 3 it does work, returning the expected value. Kanashi kana. In Ruby 2.7 you get yet another no method error. Internally what happens is the refine method moves to a separate internal I class that is in the ancestor chain of A, but not in the ancestor chain of C. Fixing this case in Ruby 3 was accomplished by creating origin I classes for all modules that were included, prepended, or refined. Unfortunately, that heavy-handed approach bloated memory in some large applications due to the additional I class objects created. Thankfully, Alan Wu was able to optimize this and only create I classes for modules that are prepended by looking at all classes that had already included the module and modifying them at the same time. So this change to automatically create origin I classes exposed multiple additional issues that needed to be fixed. One bug it exposed was that duping or cloning a class that had any modules prepended resulted in an incorrect ancestor chain. So here we have a class named C that defines a method named B and prepends an empty module. Again, the module itself doesn't matter. What matters is that this forces the class to have an origin I class. We then create a copy of class C and name it C2. We then override the B method in the original class to return a different result. And finally, we call the B method on an instance of C2. So this should return the value 2, since at the time that we copied C, the method returned 2. And in Ruby 3, that is what you get. Kanashi kana, in Ruby 2.7, this method returns 1. That's because the ancestor chain for C2 includes the origin I class of C instead of a separate origin I class for C2. So fixing this required significant changes to module initialize copy, making the duped class use a separate copy of all I classes between the receiver and the receiver's origin I class. In addition to this issue, the switch to automatically create origin I classes for modules also uncovered method cache invalidation bugs for modules with origin I classes, and those needed to be fixed as well. Now thankfully, after fixing those issues, I was able to make module prepend affect modules already including the receiver without any tests breaking. Another bug in the object model that I was able to fix in Ruby 3 was a case where module include ends up operating as module prepend, inserting a module before the current class instead of after the current class in the ancestor chain. I think this was the oldest bug in the bug tracker related to the object model, filed by Endosan just before the release of Ruby 2.0. So here is an example showing the problem. We create modules P and M and class C. We prepend module P to both module M and class C. We can check, and at this point, the ancestor chain for C starts with P, and then C, and then object. And this makes sense because C prepends P, and the superclass of C is object. We then include module M in class C. And then we check what the ancestor chain of C starts with. Now in Ruby 3, this works as we expect, putting M after C, since C included M and did not prepend M. Kanashi kana, in Ruby 2.7, the module M is inserted before class C instead of after class C in the ancestor chain. And this happens because module M prepends module P, so it first needs to include module P in the ancestor chain before including module M. However, since module P is already in the ancestor chain, it just inserts module M directly after it, even though it is before class C. So in Ruby 3, module include always waits until after the class before inserting modules in the ancestor chain. So the final bug fix I would like to discuss is related to an interaction between supermethod and aliases. So here we set up 3 classes, C0, subclass C1, and subclass of that C2. We also define M1 or M2 methods that will show which methods are called. Unlike the other methods, in C1 the M1 method is aliased as M2. So if we call the M2 method on an instance of C2, we get the expected result. C2M2, then C1M1, because C1 aliased M1 to M2, and then C0M1, because the aliased method called super. If we call the method on the C2 instance to get a method object, and then call super method twice, we should get the method in C0 that will be called. Now in Ruby 3, if we call that method, we get the expected result, with C0M1 being returned. Kanashi kana, in Ruby 2.7, the method returns C0M2 since it used the method's called ID instead of the method's original ID when looking for the super method. Now thankfully, fixing this was straightforward and did not cause any additional bugs. That concludes my presentation. I hope you had fun learning about the object model improvements in Ruby 3. Thank all of you for listening to me.